Welcome to our final learning workshop. It's actually not workshop number 9. For some reason, I have that up there. I think it's actually, in this case, going to be workshop number 12, organic chemistry. So this workshop, we are going to focus on naming and drawing structures for alkanes, alkenes, and alkynes, naming and drawing structures for aromatic compounds, and a big part of that is knowing priority, like knowing how to assign priority in terms of where do you start numbering the chain, because that will determine what type of name you give it. Also, we'll be discussing types of isomers and how to distinguish between them, and we'll be going through some of the basic fundamental reactions. Okay, so first and foremost, I did have some practice problems that that we have prepared here, but I'm probably not going to use those for the most part because they are designed to give a little bit more of a mixed and somewhat more thorough, to be honest with you, addressing of this concept, but it kind of is also a little bit more scattershot, taking a stab at a few too many concepts. And I really want to focus on the fundamental concepts here, which would be naming, isomers, and reactions. So let's go ahead and begin. So the first thing we want to go ahead and start with is the naming of alkenes. So before we even do a whole lot with that, I want to go over the levels of priority. So there are 3 levels of priority when numbering priority. Actually, I think I might be getting ahead of myself. Let's go ahead. What are the steps to naming an alkane? What is the first thing that you want to do when naming an alkane? What do you want to look for?
May I answer this question?
Absolutely, please do.
Okay, so the first step that you should take in naming an alkane is to locate and find your longest continuous chain.
Yeah. So determine the longest continuous carbon chain. All right. Number 2, what's the next thing we do?
The next step is after you would identify your longest continuous carbon chain, using that as a point of reference, identify your substituents / side groups or your branches. Mostly in this case, you're going to be dealing with alkyl groups.
Yeah, identify branches, substituents. And the word substituents comes from the word substitute. And what we're referring to is something that is substituted in place of a hydrogen. So when you have these carbon groups coming off the side, like if you had a straight chain alkane of 7 carbons long, if there's any branches off that chain, you could think of those branches as actually being substituted for a hydrogen on a base 7 carbon chain. So substituents means substituted for hydrogen. Okay, so identify branches or substituents. And we also want to make sure that we do what?
Oh, yes. Sorry. You also want to specify the location of each respective substituent with a given number.
And how do you get that number?
Oh, you would number each carbon chain that is in the longest continuous carbon chain, the main body, so to speak.
So basically what you need to do is you need to number the longest carbon chain according to the levels of priority. All right, so that gives us a nice little segue into what I wanted to talk about with regards to priority. Okay, there we go. So the levels of priority. So these levels of priority actually work for not just alkanes, but for all compounds, which is why the first level of priority is going to be number starting from the end of the chain, which is closest to the functional group. Now, obviously, if it is an alkane, there is no functional group, okay? But if there's not an alkane, then there is a functional group. You're going to start numbering from the side closest to the functional group. Doesn't matter where your branches are, if there is a functional group. Now, a functional group can be a double bond, functional group can be a triple bond, a functional group can be an alkyne, or it could be an alcohol. But you're going to start numbering your chain starting from, or you start numbering on the ring from the functional group, or start numbering the chain from the side that's closest to a functional group. All right. What about if it's an alkane if there is no functional group? If there is no functional group, as in the case with an alkane, then you're going to number from the side and a number from the end of the chain which is closest to the first branch. Now, if the first branch is equidistant, if it's equally close to either end, then you're going to have to go to the second branch. In the first level of priority, number from the side closest to the functional group. If there is no functional group, or if the functional group is in the middle of the chain, so it's equally close to both sides, then you go to the second level of priority. Number from the end of the chain which is closest to the first branch. If the first branch is equally close to both sides, then number from the side closest to the second branch. Number starting from the side closest to, so a number starting from the side closest to the second branch. So you number, and then of course, if the second is equally close, then go to the third. And if third is equally close, then go to the fourth. If the branches, if the branches have the same numbers, regardless of which end you start numbering from, number the branch number according to alphabetical order. So that's your 3 levels of priority. If first level of priority is functional group, second level of priority is lowest numbers on your branches, third level of priority is alphabetical order. Okay. So let's go ahead and do some of these. Let's do some practice problems with this. Okay, I'm going to start out drawing a complete structural formula so you can see everything that you need to. Okay. See all the structures. So complete
Yes.
12U condensed structural formula. So we have a CH3, CH. Okay. So the first thing, I would argue that the first thing that you want to do is, yeah, like you said, is determine the longest continuous carbon chain. So what's the longest continuous carbon chain? How many carbons are in the longest chain here?
Let's see. For me, so far, it appears to be 7.
Okay. So that's not quite correct. Can you see where you might have missed one? Circle go ahead and circle what you see as the longest chain. You can write on the whiteboard as well. So
Oh, okay. Let me see. I think I'll just underline it a little bit. So, a second. So for me, this is what I see. So,
okay. So one of the ways in which you can kind of check and look for the longest carbon chain is to look for any intersectional carbons. Okay. So the intersectional carbons would be like would be those that are connected to 3 or more carbons. So that this carbon is connected to 3 or more carbons. This one is connected to 3 or more carbons. All of the others are connected to only 1 or 2. Okay.
oh, okay.
So if I look for the intersectional carbons, I'm looking for the 2 longest ends, the 2 longest directions or branches off of those intersectional carbons. So like for example, with this intersectional carbon here, how many carbons are off to the right? I mean off to the left?
Off to the left, just 1 carbon.
Just 1. How many are down?
Let's see, 2.
2. How many to the right?
1, 2, 3, 4, 5. 5. Right.
Yeah. Well, yes, exactly. So I'm going to want to go with the 2 longest branches. So that means, does that change your idea?
Let me see. Sorry. So what you're saying is that, can you see my pointer here?
Yeah.
Okay, so so what you're saying is that my like main chain respectively is the hexane here?
No, that's not the main chain.
Mm.
See, because what you have to understand is even though that this is drawn like this, that doesn't mean that it actually looks like this on a molecular level. On the molecular level, these can twist and move and bend and switch around, and like the bonds can't break, but I can. This is like, think of it more as more fluid, as if it was like a rope. If it was a rope, if I wanted to grab 2 ends and pull it out to make it as long as possible, which 2 ends would I grab?
Oh, make it as long as possible. I must apologize if my like hybridization understanding is a bit off.
Well, this doesn't have anything to do with hybridization. But if I'm just looking at the 2, like for example, if I look at my CH3s here, the CH3s are my end carbons. Which 2 ends would I grab to make this as long as possible?
Oh, I would assume this end and this end.
Exactly.
Oh.
There, this is 1, 2, 3, 4. That's why I said look at those junction carbons. Look at those intersectional carbons. This one, the longest 2 directions from this one were down, because that was 2 carbons, and across. And then once I got to this one, the longest 2 ends would be up, because that's 2, and left, because that's 1, 2, 3, 4, 5. So down here is only 1, over here is only 1. So I always have to go in the direction of the 2 longest chains.
Oh, okay. I see what you mean.
Okay, so be that since that is the way that it is, Now I can go ahead and I can start numbering this chain. And I have to start I can't start numbering from the middle. I have to start numbering from one of the ends, okay?
Mhm.
And I'm going to start numbering from the side closest to a branch. Well, okay, so if I number from this side, this is carbon number 1, 2, and 3. And I see how I have a branch on 3. If I start numbering from the other side, it's 1, 2, 3. Okay, I have a branch on 3. Well, uh-oh, because now, okay, so now we're just going to have to look and see, okay, well, what about the second substituent, okay? So 1, 2, 3. I actually have 2 branches on this one, so it's actually 3 and 3. And for this one, I have 1, 2, 3. Well, that's the first substituent, but to get to the second substituent, I have to go 4, 5, 6. So the second substituent is going to have a lower number if I start on this side. Does that make sense?
Mhm.
So I'm going to go ahead and number this then. 1, 2, 3, 4, 5, 6, 7, and 8. If I number it this way, I have 3 different, and actually I should, at this point, I should go ahead and identify my branches. I should go ahead, I'm actually going to put a little square around them. 1 branch, 2 branch, 3 branch. Anything that's not part of the longest chain is a branch. Each of these are 1 carbon branches. And what is the name of a 1 carbon branch?
Um, 1 carbon branch, that's going to be a methyl group.
Uh-huh. So 1 carbon branches are called methyl groups. A 1 carbon chain is a methane. If I turn it into a branch, it's methyl. All right, so each of these are methyl groups. So then when I'm naming this, going back up to the name, now that I've numbered the longest chain according to the level of priority, in this case I use priority number 2, whichever one gives me the lowest numbers. Then I'm going to go ahead and name the compound. Starting with the branches, giving a number for each branch. For each branch. So starting with the branches in alphabetical order.
Do you want me to attempt the answer, or are you working on the answer right now?
Oh no, I mean I know what the answer is, but if you want, you can definitely attempt it. So it says, so I'm saying name the compound starting with the branches and giving a number for each branch in alphabetical order, and then followed by the name of the root chain. The root chain is the longest chain. So some people like to actually start with the end first. So what would the root chain name of this be?
Since the longest chain has 8 carbons and we are dealing with the single bonds, it's going to be octane.
All right, so this is octane. Now we also have our 3 branches. So what would we have to put for that?
Excuse me. Okay. In this case, for our branches, we'll have to specify the numbers first, which in this case is 336. Separate them with commas, then put a hyphen, and then specify the amount of methyl groups with the prefix trimethyl. All of this
Absolutely.
is in front of octane.
Uh-huh. Absolutely. So 336, 1 number for each branch. 336 trimethyl octane. 336 trimethyl octane. Very good. Let's do another example. This time I'm going to use the what's known as the bond line structure form because this is a very common form that professors like to use, and it's not as easy to see. Okay, so let's try. Actually, let's try this one. How would I name this? What's the first thing that I'd want to do?
In this case, try to identify the longest carbon chain.
So the longest carbon chain. So okay, to identify the longest carbon chain, you want to circle it for us? And just as a side note, one of the things I sometimes likes to do with these bond line structures, and I find that for some students it makes it easier to do the rest of the naming, is put a little circle for every carbon. Now every end and every corner is a carbon. So here's a carbon, here's a carbon. This is a carbon, 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 this is a carbon. Okay, so go ahead and circle the longest carbon chain.
Okay, again, I apologize if my little pencil's a bit off.
No, that's totally fine. Don't worry about it. Okay. And that is correct. And so now which side would you start numbering from? Or does it matter?
Let me see real quickly. In terms of, if I recall correctly, within this case, we are now dealing with two different functional groups. If you don't mind me labeling this like real quickly, this
Yeah,
looks
absolutely.
like
Let's label.
Yep. This looks like to be your methyl group. This is M for a methyl, and then over here in this case, this looks like to be your this is a different alkyl group, which is your ethyl for E. In terms of, if I recall correctly, in terms of the alphabetical order, you want to give them the smallest numbers. So for me, I would assume that we would start numbering from this, from my right side. Is this correct, or is my memory
Yeah,
faulty?
absolutely right. In this case,
Oh, yeah.
the second level of priority does not apply here because no matter how you start numbering, if you start numbering from the left or if you start numbering from the right, in either case, you're going to end up with the same numbers. It's still going to be 3, 5, or 3, 5. So then you go to the third level of priority, which is alphabetical order. And since E comes before M, this is going to be 1, 2, 3, 4, 5, 6, and 7. So then what would the name of this compound be then?
Let me see. It would be 3 hyphen ethyl, and then another hyphen for 5 hyphen methyl heptane, because it looks like you're dealing with single bonds respectively. So the ending's going to be ane.
Yep, absolutely. 3 ethyl, 5 methyl heptane. Very good.
Yay.
All right. So let's you want to try a couple others?
If it's possible, yes.
All right. I got some fun ones to try with you. I'm going to go ahead and clear this screen, and I'm going to share a different one. Here we go. So you can zoom in to see it a little bit closer if you wish. Let's have you start by doing the first one. Number 1.
I'm trying to zoom in. Okay, so do you want me to explain my like thought process while I attempt this?
Sure, that'd be
Okay.
great if you want to.
Okay. Okay. Sorry about that. I just wanted to make sure of that I was accounting correctly. May I circle the main continuous chain first?
Please do.
Okay. So far, the main continuous chain that I could identify here is this one.
Okay. Now, I understand why you did that, but you had a choice, didn't you?
Yes. Can you see my pointer here?
Yep. What would be the other possibility?
The other possibility that I noticed was also going this way too. 1, 2, 3, 4, 5, 6, 7.
Yeah. So with our intersection carbons, those two orange ones, when you have a situation where you have two different directions you can go and both will give you the same longest carbon chain, you always want to go in the direction of the more branched chain. And the reason is because it'll make your substituents simpler.
Ah,
So in this case, the way that you did it is understandable, but it's also not quite correct.
I see. Okay.
So let's go ahead and have you try again. Ah, look at that.
Okay.
What did I do? There we go. Draw me a new longest chain.
Oh, yes, sir. Okay, so from the looks of it, I'm pretty sure I can understand this route because initially within this case I had an isopropyl
Yeah,
group here, but now this time we have ourselves an ethyl group and two methyl groups.
yeah,
Oh, sorry. We have an ethyl group and two methyl groups. Sorry,
yeah.
my pointer wasn't working.
No problem.
Originally, I was going to have an isopropyl group. I see what you mean now.
Hmm. Yeah. Now, of course, if there had been an extra carbon here, over here, been an extra carbon
Yes.
here, you would have still gone. You would have gone in that direction, even though it's more branched in the other way. You still would have gone in that direction because that does give you the longest chain. But in a case where the longest chain is the same either way, you do always want to go in the direction of the more branched chain.
Oh, okay.
To simplify the substituents. Okay, so now which side do we start numbering from?
That was my pointer. I would start, let's see. I would start numbering from this side to produce the smallest number to help you locate the respective ethyl group.
Very good. That's exactly right. So 1, 2, 3, 4, 5, 6, and 7. So now all you have to do is name it.
Okay, so I'll just type it out here
Yeah,
on
please
the
do.
slide.
That's perfect.
And one more little detail to note as well. When you're using prefixes like di, tri, and di, tri, and tetra, when you're specifying the number of the respective side groups, in terms of alphabetical order, those are not considered at all.
Yeah, so exactly. So in this case, Alphabetical order is secondary when you're naming it. Even though the number is 3, I'm not going to put the methyls first because when I name the compound, I always list the substituents in alphabetical order, even if the number, even if it's like a 7-ethyl and a 2-methyl. You know what I'm saying?
Yes.
I'm always going to put the alphabetically first substituent first in the actual name, even if the number is not going to be lower.
I see.
All right. Excellent, excellent, excellent. All right, let's try. Let's try. Do you want to do another chain one, or do you want to move to the ring ones?
I want to see if I can go ahead and practice a bit with the. Let me see, because I have to take it into consideration time. I want to see if we can practice more with the chain ones because I feel like I need to challenge more of my sense of
Sure.
simplifying those substituents.
Got it. All right. Well, in that case, let's go ahead and have you do. Um, let's see. Should I have you do 2 or 3? What do you think? Which looks more intimidating? Let's do 2.
Yeah, let's try to. I'm going to outline my continuous chain. Here. So now that in this case I have simplified my respective substituents to where I have a chloride ion here, a bromide ion, and then I have a methyl group.
Excellent. Excellent.
Oh, sorry. I thought your mic cut off for a second.
No, no, no. You're good. You're good. Yeah, no, that's absolutely right. You
Okay.
targeted right now. Which side would you start numbering it from?
Let's see. In terms of alphabetical of order, it's going to be a B, C, and then there's M. So in this case, I would start numbering it from this side.
Yep. So I
Ooh,
got my 3 different branches. I'll start numbering from the side closest to the branch. And that's going to be put the bromine on carbon number 2, whereas if I did the other one, it would put the chlorine on carbon number 3 if I started from the opposite side. So 2 is lower than 3. I'll start numbering from the side that gives me a 2. 1, 2, 3, 4, 5, 6. Yeah. And so then what would the name of this be?
I shall type it out. Oh, sorry, give me a second. The text went off the screen.
That's okay, I'll drag it over.
Edit.
Okay, excellent. Good job. Yeah, absolutely. It's 2 bromo, 4 chloro, 3 methylhexane. You named the substituents in alphabetical order exactly the way you ought to have. So that's perfect. Very well done. It seems
Thank
like you
you.
really do have a good solid sense of these. I want to take a look at the ring ones just real quick because I think it'll give us it's a uh, slightly different situation. So if we
Let's
go
see.
down to, let's say, number 5. Number 5 is a ring. Admittedly, it's only a 3-carbon ring. I have a carbon right here, carbon right here, and a carbon right here, in addition to the methyl groups that are attached. Since a ring is a ring, you can actually, it doesn't have an end per se. So you can actually start numbering it from any point. You can actually start numbering it from any point in the ring. And so typically, you're going to start numbering from a carbon that has a substituent, a branch. But you're also going to start numbering in the direction, like in the way that's going to give you the lowest number for your branches. Okay?
Mhm.
So if I'm looking at this, which carbon might I want to put as my number 1 carbon if I want to get the lowest numbers?
I would say this one right here, the top one.
Absolutely. So this is going to be your number 1. And then which direction am I going to go? Clockwise or counterclockwise?
Counterclockwise, so that this is number 2.
Exactly. So I can actually go either direction. So I'm going to go counterclockwise. And that's going to give me 2, 3. Now, because this is a 3-membered ring, and because it is a ring, I'm going to have to use a cyclo prefix. And a 3-carbon chain would be normally called what?
3-carbon chain. Oh, I feel so silly. Cyclopropane.
Yeah, normally 3-carbon chain would be propane, but this is a ring, so it would be cyclopropane. Very good. And
Okay.
then you just name the substituents or branches just like you would anything else. So go ahead and go ahead and type out the name for that then.
Just gotta make sure I didn't do any little spelling mistakes. Okay.
Yeah, there you go.
Yep.
The chloro is alphabetically first, so it goes first. It's 1-chloro, and it's 1,2-dimethyl. Very good. Excellent job remembering to use your prefix. You can't just say 1,2-methyl. We have to say 1,2-dimethyl, or if there's 3, trimethyl, or 4, tetramethyl. But
And also one more, I'm sorry,
go ahead.
one more thing to like specify. Notice on how like unlike in the other previous cases, you're going to have to repeat like some of your numbers, so to speak.
Yeah, because sometimes you'll have more than one branch on the same carbon. Yep, absolutely. So now,
If you don't mind,
should
if
I
you don't
have you
mind,
do one more challenging one with the cyclic?
yes. However, is there a way for you to like send me these pictures, so to speak,
Oh
of these
yeah,
problems?
absolutely. I'll go ahead after the session. I'll go ahead and I'll email you the PDF of this particular document. I can also email you the PDF of the answer key if you want.
Oh yes, sir. Please.
Okay, so let's do number 6 because that looks fun.
Oh, and also, can you make sure to make it available to the students watching the recording as well?
Oh yeah, I'll post it up on the website.
Okay, thank you. Sorry, just wanted to make sure.
Yeah, no, absolutely.
Okay, so and number 6 is what you said, correct?
Mm-hmm.
Okay, so it looks like you're dealing with with a type of cuboid shape. So so your numbers are going to range from 1 to 4 in this case.
Mm-hmm.
However, though, again, because of alphabetical order, I'm going to say that we will start numbering right here at the location of this bromide ion.
Very good noting alphabetical because in this case it's going to be 1, 2, 3, and 4, or 1, 2, 3, and 4, no matter what you start with, or matter where you start. So you're going to want to go ahead and start with the bromine. And if that's number 1, does it matter if you do clockwise or counterclockwise?
Let's see. In terms of a notation respectively for the chloride ion, it doesn't matter because in this direction it's going to be labeled as number 3. If you can see my pointer,
Mm-hmm.
for example, like clockwise 1, 2, 3, 4, and then counterclockwise 1, 2, 3, 4.
Mm-hmm. So you can really do it either way, clockwise or counterchlockwise. Now, what about if this group here, instead of being a CH3 was a chlorine, which way would you have to go?
Oh, fluorine.
A chlorine.
Yes. We're going to have to go counterclockwise
Yeah, in
automatically.
that case, you'd have to go counterclockwise. But in the original compound, it was a CH3, so I don't have to worry about it. I could go either way. So we're just going to do clockwise, starting with bromine, 1, 2, 3, 4. So what would be the name of this compound then?
Okay. So I wrote, in case it's really small, I wrote down 1 bromo, 3 chloro, 2 4 dimethylcyclobutane.
Absolutely. So it's 1 bromo, 3 chloro, 2 4-dimethyl cyclobutane. Butane is the root name for a 4-carbon chain. It's a cyclobutane because it's a 4-carbon ring, and we labeled the substituents in alphabetical order. Perfect. And the same rules that apply for naming and putting substituents on cyclic aliphatic hydrocarbons, we can also apply that same naming principles to organic or aromatic carbons, aromatic compounds, such as 7, 8, or 9. So, for example, for 7, when you have a 6-membered ring that has like this ring in the center, the ring in the center, sometimes this is also drawn like this. I'll go ahead and draw it alternatively. You can also see this drawn like this, and more commonly you do see it drawn like this, where it's alternating double and single bonds. Now the reason sometimes you put a ring in the center is because with alternating double and single bonds, they have what's known as resonance, and the resonance can cause basically these, alternatively, you could put the double bond down here, which would cause this double bond to go here, which would cause this double bond to go here. And the truth is, what's really happening here is that these 6 pi electrons, these 6 electrons that are in the ring, are actually delocalized. They're not actually on between any specific 2 carbons. They're just continually swirling around in the middle. So the ring is actually, the ring on the left is actually a more accurate way to represent it. But for the purposes of more clearly representing exactly how many pi electrons are in the ring, the double bonds are helpful. Okay, so in this case you have 2 methyl groups. They're both attached to the ring. This ring, aromatic ring, gets a special name of benzene. Benzene, B-E-N-Z-E-N-E. And then you would name the substituents before the benzene. In this case, I can start numbering from either end. It doesn't matter because they're on opposite sides. So this will just be 1, 2, 3, 4. And in that case, I will just call this 1,4-dimethylbenzene. 1,4 dash dimethylbenzene. A comma between numbers and numbers, dashes between numbers and letters, and or hyphens if you've heard, as opposed to dashes. Yeah, Victoria has a natural knack for knowing where to put the commas and where to put the hyphens. But for those of you who are a little bit less familiar with this, it's always the commas between numbers and numbers, dashes between numbers and letters, and no spaces. Excellent. So let's see. Why don't I have you take a stab at number 8, and then we'll switch to something more interesting.
Okay. So for number 8, as we could tell, we have ourselves this respective benzene ring. However, though, you have yourself 2 different side groups, your methyl groups again, and your halogen chloride ion. So in terms of numbering, in this case, again, alphabetical order, I would start here as your number 1. However, though, notice on how, like, in either direction that you would go, your methyl groups will have the same number. So, for example, if you don't mind me, Mr. Dupal, if I can label the numbers. Did you hear me?
Yeah.
Okay. Sorry. Just making sure. If we put this as number 1, and then we go clockwise with 2, 3, 4, and then 5, and then 6, and then if
now before we go any further, though, let's think about what are our levels of priority.
Sorry, levels of priority. So far in this case, it is to try to number the branches in a way in which you would produce the smallest numbers.
Yes, smallest numbers. So is there any way to number it that you get smaller numbers than 1, 2, and 6?
Oh, 1, 2, 3, 6. No, because regardless of which way that you would go, you're going to get 2, 1, 2, 3, 4, 5, 6, the same
Ah,
notation for both of your
you,
methyl groups.
but do you have to start numbering on do you have to start numbering on chlorine?
Hmm.
You
I'm
actually
sorry, am
don't.
I like incorrect?
You are.
Oh,
That's
darn, I'm
okay.
sorry. I'm
No,
sorry.
we all make mistakes, and yeah, in terms of like you don't have to start numbering from chlorine. Chlorine isn't a functional group. If it was an OH, then yes, you would. Chlorine's not a functional group. It's just a halogen branch.
Oh, I got myself mixed up again. Sorry.
No, that's okay. So the second level of priority is lowest numbers, and so to make it the lowest numbers, where did you have to start numbering it?
Uh, 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 I would start numbering it from one of your methyl groups then.
For one of the methyl groups, yeah.
Oh, I feel
Yeah.
so silly. Sorry.
No, it's okay. And see, these problems, these problems, particularly on this sheet, are problems that I specifically designed to mess students up, like to get them to make these mistakes so that they can learn from them. Because usually you are not in a position where you end up having to deal with these types of things. But every now and then you'll get a compound that shows up either on a test or a quiz or in homework that does require you to make these distinctions. And so I created these problems specifically to deal with those situations where students would be likely to make a mistake on it if they didn't know these, you know, these things, these rules, the level of priority, etc.
Okay, I see. I see. Okay, I just get nervous with you because again, I'm a bit of like a perfectionist when it comes to like trying to get like everything right, even though I know that's not possible.
Yeah, no problem. Well, hey, I can tell you that I've always learned more from my mistakes than I have from my successes. Uh,
It's true.
the one of the two of the classes that I did the absolute worst in college are classes where I actually learned the most. So in terms of grade wise, yeah, I got the worst grade of my college career in those classes, but I actually ended up learning the most.
I understand.
So it and that's really ultimately the most important thing. But no, this is good. This is good. Gives you an opportunity to, and that's the whole purpose of the workshop. Gives you an opportunity to make mistakes so that you can learn from them and be better and stronger. You've actually impressed me at how much you know already and how few mistakes you're actually making. Usually, I would have had students fall for like several additional things that you have correctly done. So well done on that.
Oh, nice. Thank you.
Okay, so now then what would be the name of this compound?
I believe the answer would be 2-chloral 1,3-dimethylbenzene.
Yeah, 2-chloral 1,3-dimethylbenzene. Yep, very good. All right, so now let's go ahead and I want to take a moment to distinguish between different, well, okay, let's just do a little bit with naming and drawing alkenes, and then I want to try to get to, or rather, let's do a little bit with isomers, or in naming and drawing alkenes, and then I want to try and get to isomers and distinguishing between isomers. So let's take a second, and I'm going to go ahead and share whiteboard. Okay, so alkenes. Let's say I was to have something like this. Okay, say I had a compound like this. Which side would I start numbering from?
You would start numbering from my right side.
Exactly, because in this case, the functional group is the highest priority. And the functional group in this case is the double bond right here. If I number from this side, it'd be 1, 2, 3, 4. With 4 carbons before I get to the double bond, but on the other side, it'd be 1, 2, 3. It's only 3 carbons before I get to the double bond. The left-hand side is, the right-hand side is closer to the double bond than the left-hand side is. So I must start numbering from the right-hand side. Now notice, this is despite the fact that the bromine is on carbon number 2 and the double bond is going to be on carbon number 3. That doesn't matter because the functional group is always the most important thing in the molecule. So I have to start numbering from the functional group, from the side closest to the functional group. Now when I'm numbering alkenes, there we go. Now when I'm numbering an alkene, or when I'm giving the number for an alkene, you'll notice that the double bond is actually between 2 carbons. It's between carbon number 3 and carbon number 4. Which number do I give the alkene when I name it?
3, the lowest number.
3. Yeah, you give the lowest number. So, and this is how many carbons across?
7 carbons.
So this is going to be a 3.
3 heptene.
3 heptene. At least that's the old IUPAC naming system. There is actually a newer updated version which you can use as well. If you wished, you could also call this hept 3 hene. But most of us old timers still stick with the 3 heptene.
Oh yeah, within my respective class, my professor still uses this version instead of this.
Yeah, and both are acceptable. But both are acceptable. This is the this one is the newer IUPAC regulations, but the older ones are still acceptable. Because so this is 3 heptene, but in addition to the 3 heptene, I also have to put what?
Let's see. You'll also have to specify the location of your halogen here, which will be 6-bromo-3-heptene.
Yeah, 6-bromo-3 heptene. Very good. Very good. Absolutely. So what about if you had something like this? If you have cyclic alkene like this, where do you have to start numbering?
Let's see. In terms of the direction over here, it looks like that you have yourself an alkene or a double bond occurring over here. So for me, I would start numbering around within this point.
Okay, so here's your number 1 carbon, right?
Mm-hmm.
Right.
Sorry.
Now, which way would I go? Would I number clockwise or counterclockwise?
Counterclockwise to create the smallest number of used to specify the location.
Your branches. Yeah.
Yes.
Now, unfortunately, in this case, you would have to your number 1 and your number 2 carbons in a ring must always be your alkene carbons.
Alkenes. Yeah, I just noticed that.
Even if it would give you lower numbers on your substituent, you do have to have 1 and 2 be your alkene ones. But you would have to actually start with the number 1 on top rather than having the 1 over here. So it's interesting because sometimes students want to do what you did, which is to start with the number 1 there and then do counterclockwise. Can't do that. But then students, when they hear, okay, well, maybe then what I want to do is start over here and have a 1 here and then a 2 here. And then this could be a 3, and it'll be 2,3-dimethyl rather than 1,6-dimethyl. But you actually know you have to do 1, 6, because it's the first. Remember, in the numbering, the second level of priority, it's whichever gives you the lowest number on your first branch. So it's better to have a 1 on carbon, a 1 for your first methyl group, than to have lower numbers overall for your methyl groups.
That's right, because you are supposed to number sorry, you should be able to give like the smallest numbers to your respective like functional groups. It is first priority. Sorry if it like sounds like I'm just reiterating what you're saying.
No, it's good. It's good. These things need to be repeated, but yeah, absolutely. So, and anytime you have a cyclic alkene, your numbers 1 and 2 have to be the alkene carbons. So this is going to be 1, 6, dimethyl cyclohexene. Pretty cool, huh?
Indeed. Ooh, sorry.
All right, so now that we've gone through that, I want to briefly take a moment. I want to take some time to go through the isomers since we only have about 15 minutes left. I want to create for you a little flow chart on isomers. Okay, so if you're trying to establish what type of isomer it has, there's a series of questions you can ask yourself that can help you distinguish whether or not the isomers and what type of isomers they are. The first question you should ask is, do they have the same number of atoms of each type? So if they have the same, so there's two possibilities here. Got to be yes or no. If the answer is yes, then you have an isomer. We just got to figure out what type of isomer it is. If the answer is no, then that means the two compounds are not isomers. Do they, and I should edit this, so do the compounds have the same number of atoms of each type? If no, they're not isomers. If yes, the next question we have to ask yourself is, are they connected? Or actually, I should say more specifically, are the same atoms connected to the same atoms? In other words, do they have the same connectivity? Do they have the same connectivity? And if the answer is yes, then we have more questions. If the answer is no, then that means we have structural isomers. So no. We don't have the same connectivity if the same atoms are not connected to the same atoms. In other words, it's not a carbon connected to another carbon, which is connected to two other carbons and an oxygen. If the same atoms are not connected in the same way, then structural isomers. So, structural isomers. If the answer here is yes, then we have to ask ourselves another question. And that question is, are they non-supersymmetric Impose. Oh, actually, are they mirror images of one another? Are the compounds mirror images of one another? And once again, we have yes or no with our possibility. Okay. So yes. Sorry. If they are mirror images of one another, that leads us to got thrown off track. Sorry. That leads us to one last question. If they are not mirror images of one another, if they're the same connectivity but they are not mirror images, then that means that they are what are referred to as diastereomers. And diastereomers include cis trans isomers, but are not limited to them. So diastereomers are not just cis trans isomers; they also include other types of isomers as well. On the other side, if they are mirror images of one another, we have to ask, are they superimposable? Are they superimposable? In other words, can they be rearranged so that they can actually perfectly fit right on top of the other as like basically the same thing? Are they superimposable? Are they basically the same compound essentially? If the mirror images are superimposable, then that means you have, so if yes, then they're the same compound. If no, that means they're enantiomers. So if yes, means they're identical compounds. In other words, they're the same thing. If no, if they are not superimposable, then that means that they are enantiomers. And enantiomers are sometimes also called optical isomers because they rotate a plane of polarized light. So I don't know if this helps at all, but I think it potentially can. This is how you distinguish between structural isomers, diastereomers, and enantiomers.
Mr. Japal, this is really, really helpful. Don't worry. My biggest, to me personally, isomerism in terms of like concepts and problems looked a bit more intimidating for me. And trying to like remember most of the main differences is much more organized, so to speak, with this little flow chart. So again, thank you very much.
You're welcome. You're welcome. Now, admittedly, the difficult thing about stereoisomers is that it does sometimes require you to think in three-dimensional terms, and that can be challenging. So let's go ahead and go through a couple of examples. I actually think that there is a good example on the original workshop outline that I was planning on using. I'm gonna. Do you need to take a picture of this or a screenshot before I?
I already took a screenshot just now. Thank you.
Okay. Yeah, no problem. So I'm going to go ahead and cancel this, and I'm going to go share. Let's see. So going back to our, okay, let's see. Okay, let's go up here. Which of the following compounds are capable of isomerism? And in each case where isomerism is possible, identify the type or types of isomerism. So in the first case, like if I'm looking at A, 2A, is there any other way that I could arrange those atoms and have them bonded together?
Sorry, will this information require my understanding of, um, sorry, can you see my cursor or my pointer?
I can't.
I understand, sorry, I was able to
That's
do that
okay.
earlier.
So it's kind of like this. So basically think about it like this. So for A, oops, down here, could I, instead of having a branch there, could I have this just as a chain of 5 carbons like this?
Oh yes, indeed.
Yeah,
Um,
that
sorry,
would be
I was
possible,
more
right?
focused
Have
on this.
Mhm.
Oh,
I could
oh,
still have the
sorry.
NH3 here. Still have the NH3 here. I could still have the hydrogen here. And instead of having um, the 3 other carbons be like split like that, I could have them all in a chain, couldn't I?
Yes.
So is this capable of structural isomerism?
It appears so, yes.
Yeah, so this could have, so A could have structural isomers. Now, what about cis trans isomerism?
Cis Trans Isomers.
It doesn't
That looks
appear like that would be possible, right? Because there's no double bond.
Yeah, it doesn't look possible.
So it's not going to have cis trans isomerism. It's not, so then I have to look at, does it have a chiral center? In order for something to have optical isomerism, it has to have what's known as a chiral carbon, and or a chiral center. Usually it's a carbon, a chiral carbon, and a chiral carbon is a carbon that is bonded to 4 different groups. So as a general rule, if I'm looking at this carbon here, this carbon here can't be chiral because it's already bonded to 3 hydrogens. Well, that's 3 identical groups. I need 4 different groups. So that's not chiral. Likewise, this one can't be chiral, bonded to 3 hydrogens. This one is not perhaps as easy to see. I do have 1 hydrogen. Okay, that's fine.
You have
I have
2
one.
methyl groups.
Yeah, that's the problem. I have a methyl group here, and I have a methyl group here. So that actually does not have 4 different groups. 2 of those groups are the same. So then I can look at this carbon. And what about this one? I look at the 4 sides. That hydrogen, not the same as NH3, right? And that NH3 is not the same thing as that carboxylic acid group, right?
And then over here, it looks like you have yourself an isopropyl group.
Yep.
So that is chiral.
So that actually is a chiral carbon right there. So does this have optical isomerism then?
Yes.
Yes, it does. If it has a chiral carbon, then that means it has at least 2 different optical isomers that it could have. So optical isomerism is possible here. So structural and optical are possible with this amino acid. All right. What about B? Can that have structural isomerism? Could those atoms be attached in any different way?
Yes, they can be.
Yeah, the chlorine could be on the opposite side of the carboxylic acid group. It could also be right here instead, right? So structural isomerism is possible with this compound. What about cis trans isomerism?
Ooh, cis trans isomerism. we do, it's a bit more tricky with this one because it's a benzene
Yeah.
or a molecule.
Yeah, you can't mess with the benzene double bonds. So
Yeah. So the only double bond that you could work with this case is the one between. I wish that I could like point this out. Is the one between the oxygen
yeah.
and the carbon.
But
Do you understand what I
unfortunately,
mean? Yeah.
yep. But unfortunately, for something to be able to have cis trans isomerism, you have to have two different groups bonded to each double bonded atom. And
Yeah.
oxygen is not capable of having any groups attached to it.
It looks incomplete, so to speak.
Yeah. So in other words, if you flip this over, if I switch sides, if I put the OH and the benzene ring on opposite sides, it would still be the same compound
Ah.
because there's no difference on the oxygen side. Oxygen doesn't have anything attached to it. And in
Okay.
fact, oxygen cannot have anything attached to it because oxygen typically only forms two bonds for the most part. All right, so it looks like the only thing that we have for this one is going to be structural isomerism. Ah, okay, so structural. All right, what about C?
Okay.
Can that have structural isomerism?
Um, um, uh, for me, I would say yes because you can move the double bond between the respective carbons.
Or if this five-membered ring is actually an isomer of it.
You could also, oh,
It
sorry.
has the same number of carbons and same number of hydrogens as the alkene below. Even though this one's a cyclic alkene and that one's an alkene, their structural isomers stay the same number of each atom. So absolutely, you could have structural isomers. You could also move the double bond, as if you said, as you mentioned. But and this is a little bit harder to see, but if you look at those double bonded carbons, there is a hydrogen attached to one, and there's also a CH3. And on the other one, there's a hydrogen attached to that double bonded carbon and a CH2CH3. So are there two different groups
Yeah.
on the right-hand double bonded carbon?
On the right side,
Yeah,
respectively.
this one.
Yes.
Yeah, there's two different groups attached to it. And are there two different groups attached to the left-hand double bonded carbon?
Yes.
So even though they share, even though the left-hand one and the right-hand one have one in common, the hydrogen, each of those double bonded carbons has two different groups. And therefore, can this have geometric isomerism?
Yes.
Yes, it can have what's known as cis trans isomerism. If the two hydrogens are on the same side, it's cis. If they're on the opposite side, it's trans. Now I drew the cis isomer, but you could have had the trans isomer. It's not clear from the picture and see which one it is. So it looks like you have, it looks like for that particular compound, see, I have both structural, and geometric isomerism possible. What about optical isomerism?
Optical isomerism. We'll have to see if one of our carbons is bonded to at least four different types of, like I would say, substituents, so to speak.
Yes, four different types of four different groups, yeah. And do any of those carbons have four different groups attached?
Just checking to make sure. One, doesn't look like it, no.
No. And in fact, just as an automatic rule, anytime you have a double bond, it automatically precludes those carbons that are double bonded from being chiral. because if you have a double bond, it can automatically only have 3 groups attached to it. It can't have 4 groups attached to it if there's a double bond. So, so the only ones that I could even consider for being chiral would be this one here and these 2 over here. But since each of them are connected to 2 or more hydrogens, they obviously don't have 4 different groups attached to them, and therefore they would not be chiral. So no optical isomerism. Okay, let's look at D. D. Is there any other way to arrange those atoms to give us a structural isomer?
Oh, none at all, so to speak.
Yeah, there's no way to rearrange that, because if I move one of those carbons and attach it to a different carbon, it still gives you a 3-carbon chain. There's nothing you can really do with that to give you any sort of an isomer. So in this case, this will have 0 structural isomers. It's the only type of isomer, that is the only version of itself it can be. So no structural, no optical, no geometric. Well, anyway, I hope that was helpful. I hope that helped to break down the different isomers and make sense of those. It does not look like we're going to have time to get into the chemical reactions part of this. However,
that's okay.
Before I kick you to the wind, shame on me, it's kind of a terrible way of saying it. Before I move you to move on to something else, or rather before I let you go, I do want to share something with you real quick. If you go to Chemistry Web Resources, and you go down to, or rather Chemistry Gen 12, you go to Video Tutorials under Organic Chemistry, there's actually a lot of additional practice and other videos to help you with naming and writing formulas, because we were only able to do a very limited amount. Naming alkenes, doing cis trans notation of alkenes, and also some of these reactions. So hydration of alkenes, hydrogenation of alkenes, halogenation of alkenes, and other addition reactions of alkynes. And I don't think you'll have to do anything with substitution of aromatic compounds, but there's some of that there too as well. There's also more with different reactions that can be done of all the different functional groups. And of course, you said you weren't doing any of the esters or amines or amides or any of that kind of stuff. There's also a good little section on chirality and biochemistry. So anyway, I just wanted to show you there's lots and lots and lots of really good videos that cover the basics of organic chemistry.
That is amazing. Thank you very much. How would I get access to this link again?
All you have to do is go to our website. It's actually there's a link to the website in the email that I sent to you, but also otherwise you could just Google this. Google TCC SE Science. You don't even have to do Learning Center. You can just do TCC SE Science.
Is it?
You type that into your search engine. It'll actually work with pretty much any search engine, Bing, Google, whatever, DuckDuckGo, whatever you happen to use, and that will pull up our website. It'll be a Google Sites, and then from there you can go ahead and you'll be able to pull it up.
Oh, okay. So I'm on the TCC SC Science Learning Center page. I'm on Chemistry Web Resources.
Yep.
Did you click under OChem 1?
No, I actually clicked under General Chemistry 2 under Video Tutorials. So General Chemistry 2 Video Tutorials, if you click on that.
Oh, I see the intro to organic chemistry.
Yep.
Okay. I see it. I got it now.
Yep. Excellent. Okay. Well, thank you so much for coming. It was great having you all here, and we will see you next time.